Tuesdays are the worst days of the week. Okay, we're looking here at a little bit more regarding torque and some of the properties about it. In our last video, we looked at how if we have some sort of object with a pivot, if we were to apply a force at some position, we really think about that force acting from the pivot in terms of trying to figure out what direction our torque is. Remember, that's our moment arm. And we take the cross product of these things, R cross F, as vectors, and figure out what the angle between them is. In terms of a right-hand rule, which is something we used, we place our fingers across the first vector or along it, the moment arm, and then we curl our fingers to the force. So in this case, our force is kind of pointing out of the screen. Another way to do this with a right-hand rule is if we kind of take a look at this flywheel down here, we see on the flywheel that there is a force acting on it this way. A force acting on the flywheel like this is going to cause the entire wheel to rotate around like this. What we can do as another right-hand rule is if we turn our four fingers in the direction of that rotation, our thumb will point along the direction of the torque, okay? And typically, we say that if a torque is causing a counterclockwise rotation, that's a positive torque. And if a torque is causing a clockwise rotation, that's a negative torque. Just like you would do angles in your math classes. Counterclockwise being positive angles, clockwise being negatives. Okay. One other thing we'd like to talk about here is the idea of a center of gravity. Sometimes I'll also call this a center of mass. So instead of abbreviating as COG, maybe I'll abbreviate it sometime as the center of mass, which would be a COM. Same idea, same thing. For the center of gravity and the center of mass, what we can do is if we take an object like a hammer, swinging around a hammer on my expensive computer equipment, this hammer's mass is distributed all the way from the butt of the handle all the way up to the tip of the metal head. And because of this, it would normally be hard to just push the hammer and get the whole thing to move. But at a specific point on this hammer, we can pretend that all of the mass is located there, and it would act as just a point mass instead. And for our hammer, or any object really, a quick way to find it is just to take your two fingers, hold them at the edge, and then bring them in towards each other. And wherever they start to meet, you'll find that that point, right about here for our hammer, is the center of mass. And at this point exactly, my hammer is in an equilibrium position. The amount of torque trying to pull it from this side down and rotate it like this is balanced by the amount of torque on this side trying to pull it down and rotate it in the opposite direction. Even though the head is so much heavier on the hammer, its moment arm is much shorter. It's only a little bit here. This mass on this side over here is much smaller than the mass up here, but because it's spread further and further away, it can provide just as much torque to keep this in a balanced position. Now, if we draw a little hammer right here, let's draw a hammer. A little whoop, little brimph. This is a poorly done hammer, by the way. This is not like an art class. So there's our hammer, and we found our center of mass to be somewhere right about here. Now, like I said, this means that the torque acting on this side, this counterclockwise torque, and the torque acting from this side going this way, our clockwise torque, were going to be equal and opposite. And if we summed the torques here, they would come out to be 0. Now, what's nice about this center of mass is we could go back and use it for F equals ma, thinking that our entire hammer was just a single point in space. And when we discussed free body diagrams earlier in this year, this is what we did with the center of mass. Well, what's nice about the center of mass from a torque perspective is if we had a different pivot point, let's say I held the hammer just down here at the end and allowed it to rotate. Well, which way do you think it would rotate here? It's going to rotate like that. And if we draw our pivot here on the hammer is down here, so here's our pivot. What we may have to do, and what may come to your mind, is if we wanted to find the amount of torque acting here, well, we'd have to go to each individual piece of mass along all of the different moment arms, which would mean that there'd be a piece of mass here in a moment arm, and there'd be another piece of mass in another moment arm, and more mass in moment arms. And we'd have to do torque over and over and over and over and over again. And I'd go slightly insane. What we can do instead is, if we assumed that all of the mass of the hammer existed exactly on that center of mass, we could say that the entire hammer's weight was acting at the center of mass. And then the only moment arm we need to consider is from the pivot to that center of mass. This will allow us to get a torque on the hammer in just one quick motion without having to sum up or integrate an infinite number of mass particles at an infinite number of displacements or moment arms. So that's a nice thing about the center of mass there. Now for the hammer, that center of mass is kind of shifted to one edge because the hammer is kind of a funky shape. But if you have a more uniform object, and by a uniform object, imagine like a 2x4 or just a rod of metal. If it's a perfectly uniform object where the shapes are symmetric and the density is even across all of it, then our center of mass will just be in the middle of it. So if our pivot was once again like over here on our left-hand side, the moment arm would just go halfway along the length to the center, because that's where we could think about the object's weight. And depending on your object, that center of mass may change. It's something that you just have to know based off the object. Maybe you'll be given it, maybe you'd have to figure it out in a higher level math class. Most of the time we'll be dealing with uniform objects in here where the center of mass will be just the center of the object. But if you did have some funky shape, like our hammer here, it could be offset by some bit. But that's just how a center of mass can assist us in the worlds of torque and what's going on here. Remember, we could use a right-hand rule, R crossing F, or we could just turn it in the direction of the rotation. And that center of mass tells us how an object itself is going to act underneath a torque. Hope you enjoyed that. Hope it was helpful. Check out the other videos and stay safe out there. Adios.